Welcome again to today's class. This day we want to look into classification of organic compounds. In the video before this, we discussed introduction to organic chemistry. We also see ways of representing organic compounds. Then we want to see classification of organic compounds in full. Now, this video classified organic compounds into four. One, it classified it as aromatic. It classified it into aromatic. Then it also classified it into aliphatic. It also classified it into polycyclic, and it also classified into heterocyclic. Now, under aromatic, it is subclassified into purely aromatic and non-aromatic. Now, this non-aromatic have a special type of it called anti-aromatic. So, purely aromatic compounds are benzene compounds and also other derivatives of benzene. Why do we say that benzene compound drawn this way? And its derivative, this is benzene. The derivatives of benzenes are, we have phenol, we have nitrophenol. Okay, this is nitrobenzene. Then we also have toluene. This is toluene. This is nitrobenzene. This is phenol. Then we also have benzaldehyde. This is called benzaldehyde. Now, these are taken to be derivatives of benzene. Derivatives of benzene. This is called nitrophenol. Now, these derivatives of benzene are known to be aromatic. Why? It is because they have or they exhibit resonance. That is, there is alternation of double and single bond. Double bond, single bond, double bond, single bond, double bond, single bond. Okay? There are other substances that also exhibit aromatic or that are aromatic. Substances like this substance is also known to exhibit aromatic or aromatism principles. Why do we say that these are examples of aromatic compound? Also, these compounds are also known to exhibit this. Why do we say that these are aromatic compounds? Before a compound is said to exhibit or to obey aromatic principle, it must obey these four conditions. One, it must be cyclic, it must be planar, it must be conjugated. Also, it must obey Hooke's rule, 4n plus 2 pi electron. So it must obey this rule. These four rules or four conditions must be met before you say that a compound is aromatic. Let's check now. Benzene is cyclic. From the structure of benzene, is cyclic, is planar, is conjugated in the sense that double bond, single bond, double bond, single bond, double bond. Now, it obeys Hooke's rule. Why do we say so? When n is 0, we'll be having 2 pi electron. When n is 1, we'll be having 6 pi electron. When n is 2, we'll be having 10 pi electron. When n is 3, we'll be having 14 pi electron, and so on. So, if the number of electrons in that compound falls in any of these, same with when you get to n equal to 4, then it means that it obeys Hooke's rule. Now, that is for aromatic. If you check any of the derivatives of benzene, you see that is cyclic, is planar, is conjugated, double bond, single bond, double bond, single bond, double bond, single bond, and is obeying Hooke's rule. What does Hooke's rule say? We say it must have any of these pi electrons. Now, for benzene, how many pi electrons does it have? 2, 4, 6. It has 6 pi electrons. It falls in here. Now, this one have 6 pi electrons. But does it obey Hooke's rule? Yes. Hooke's rule says it must have any of these pi electrons. So it has these pi electrons. Now, is it cyclic? Yes. Is it planar? Yes. Is it conjugated? Single, double bond, single bond, double bond, single bond, double bond. Now, here, it nearly wanted to fail the rule. But because of this plus attached at this point, it makes it to pass the Hooke's rule or the conjugated rule or conditions. Now, for this propane, cyclopropane, it has 2 pi electrons obeying, that is, this double bond, this second bond inside is pi bond. So it means that when you have double bond in a structure, one will be sigma bond and the other one will be pi bond. So what happens now is that it has 2 pi electron. 1 pi bond gives rise to 2 pi electron. If you have a structure this way, for instance, this is sigma bond, while this is pi bond. The pi bond gives rise to 2 pi electron. The sigma bond gives rise to 2 sigma electron. So 2 pi electron is gotten from a double bond in any compound. So if you have this now, 2 pi electron is falling here, then is it cyclic? Yes. Is it planar? Yes. Is it conjugated? Double bond, single bond. It nearly failed the rule, but because of this plus put here, it passed the rule. Then we go to non-aromatic. This non-aromatic, we said it has a special aspect of it called anti-aromatic. When do we say that a compound is anti-aromatic? When a compound failed the rule number 4, which is Hooke's rule, is said to be called anti-aromatic. Take for instance, we have this structure. We have this structure. So, look at this structure. This structure, we ask ourselves, how many pi bond? Is it cyclic? Yes. Is it planar? Yes. Is it conjugated? Yes. Double bond, single bond, double bond, single bond, double bond, single bond, double bond. So it's conjugated. Does it obey Hooke's rule? No. It has 2 pi electron, 4 pi, 6 pi, 8 pi. We don't have room for 8 pi electron. So it does not obey Hooke's rule. We say it is anti-aromatic. So this is anti-aromatic compound. It is called anti-aromatic compound because it failed the rule number 4. Only the rule number 4, when failed alone, it makes this compound to be anti-aromatic. Then, when do we say that a compound is, another example of anti-aromatic compound is butadiene. This is cyclic, this is planar, this is conjugated, double bond, single bond, double bond, single bond. But the issue here is that it does not obey Hooke's rule. So here, it is also anti-aromatic. Then when do we say that a compound is non-aromatic? When the compound fails any of these above conditions, any of the above conditions, when it fails it, it is non-aromatic. But when it fails only the rule number 4, it is anti-aromatic. Then, example. This is cyclopropane. It is cyclic. It is planar. But is it conjugated? No. Because it is not conjugated. This is double bond, single bond, no double bond again. So it is not conjugated. Then you ask yourself, does it obey Hooke's rule? Yes. How many pi electron? 2 pi electron. He obeyed Hooke's rule, but he failed conjugation rule. So this is non-aromatic. Then we go to the next type of or class of organic compounds, aliphatic. Now, if you classify this aliphatic based on their spatial arrangement, you'll have stretching. You also have alicyclic. Alicyclic simply means combination of aliphatic stretching and stretching or branching with cyclic aspect. Then we also have branch chain. So under alicyclic we have cycloalkanes, cycloalkynes. Okay? Then all these are so for cycloalkane, he has this general molecular formula of CnH2n. Why this one is CnH2n minus 2? Why this one is CnH2n minus 4? That means that any cycloalkane, alkene, and alkyne must have deficit of 2 hydrogen atoms than the normal alkane, alkyne. See what we mean? This is alkane. If you have C4H8, H10 please. Because for alkane only, it has CnH2n plus 2. This is the molecular formula of alkane. So when N is 4, 2 times 4, 8 plus 2, 10. We have H10. Now, when you put this in cyclic form, you have hydrogen, 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 hydrogen. Here, carbon will be here, 4 carbons. Now, how many hydrogen do we have? 2, 4, 6, 8. 8 hydrogen, giving you C4H10, H8. That means that this is having deficit of 2 hydrogen. Here is 10, here is 8. That is what we mean by cyclic form, cycloalkane. Cycloalkane must have deficit of 2 hydrogen. Cycloalkane, deficit of 2 hydrogen. Cycloalkane will have deficit of 2 hydrogen, as case may be. Then we continue on this classification of organic compounds. We say another one, this branch chain, it can be, this thread chain can be propane, propene, propyne, ethane, ethene, ethyne, and so on. So it can be with one of single bond, double bond, and triple bond, etc. Then when we talk about polycyclic compounds, it's divided into two. Polycyclic compound is divided into two. Polycyclic aromatic compounds and also polycyclic non-aromatic compound. What examples do we have for polycyclic non-aromatic compounds? When we are talking about polycyclic non-aromatic compounds, we remember naphthalene. Naphthalene, that is 2 benzene ring. 2 benzene ring. This is naphthalene. Then we also remember anthracene. We also remember anthracene. Let's write it down. This is naphthalene. Then anthracene is 3 benzene rings. Anthracene. Why do we say that they are aromatic? Polycyclic because you have two benzene rings. Then aromatic because it obeys these 3 rules. It's cyclic, it's planar, it conjugates double bond, single bond, double bond, single bond, double bond, single bond, and so on. Then pi electron. How many pi electron? 2, 4, 6, 8, 10. It has 10 pi electron. This one 2, 4, 6, 8, 10, 12, 14. It has 14 pi electron. So it obeys aromatic principles. Then for polycyclic non-aromatic compound, what example do we have? We have pentylene. Okay, this is pentylene. This is an example of polycyclic non-aromatic compound. Why? It is cyclic, it is planar, it is not conjugated. Why? Double bond, single bond, double bond, single bond, double bond, single bond, double bond, single. So it is conjugated. But does it obey Hooke's rule? No. It has 4 pi bonds, so it has 8 pi electron. Do we have 8 pi electron here? No, it has 8 pi electron. So 8 pi electron is not here. 2, 4, 6, 8. So the double bonds we have here gave us 8 pi electron. So it does not obey Hooke's rule. So it's polycyclic non-aromatic compounds. Then we go to heterocyclic non-aromatic compounds. We go to heterocyclic compounds. They are divided into 2. heterocyclic aromatic compounds and now, what are heterocyclic aromatic compounds? What do we mean by heterocyclic? Heterocyclic simply means that it contains other atoms such as oxygen, nitrogen, sulfur, etc. So, in their rings, it has these atoms. Then, what examples do we have? We say under heterocyclic aromatic compounds, we have pyridine, which has nitrogen here. Then this is called pyridine. This is furan. Furan. This is furan. Then this is pyro. So this is pyro. And so on. Other examples are thiophene and so on. Now, it is noted that pyro have more aromatic principle or is more aromatic than furan. Why? Because the nitrogen atom it contains is less electronegative than oxygen. So because it's less electronegative than oxygen, it's said to be more aromatic than furan. What are examples of heterocyclic non-aromatic compounds? For heterocyclic non-aromatic compounds, please watch their structure here. We have thietane. Thietane. We also have thyrane. They are cyclic, but they are not conjugated. Cyclic, no conjugation, so they are non-aromatic. We also have thiolane, 5-member ring. Thiolane. This thiolane is put this way. And so on. Other examples are thiene and so on. So these are ways we classify organic compounds. Now, organic compound can also be classified based on degree of saturation. Degree of saturation. Under degree of saturation, we say, okay, under degree of saturation, we say that they can be saturated or they can be unsaturated. For saturated aspect, we have alkanes and cycloalkanes. Why do we say that they are saturated? It's because they have only single bonds all through. So all saturated hydrocarbons such as alkane especially undergoes substitution reaction, chlorination reaction, combustion reaction. For the combustion reaction of alkane, CH3, look at the equation, plus X plus Y over 4 oxygen to be giving you, to give you X CO2 plus H plus Y over 2 H2O. That is a well-balanced equation or formula for balancing alkanes reactions or combustion reaction. So if here is 2, following the principle that all alkane obey this general molecular formula of CnH2n plus 2. So if this x is 2, you say 2 times 2, 4, 4 plus 2, 6. So if you have C2H6, 2 times 2, 4 plus 6, plus, you now say 2 here plus 6 over 4. 6 over 4 will give us 2 plus 6 over 4 will be giving us 2 plus 3 over 2. That will be 7 over 2. So it will be giving us 7 over 2 oxygen. Then X is 2. 2 over 2, 1. So S is 2. We now say 2 over 2 is 1. S is 2. We have 2CO2 place plus Y is 6. 6 over 2 is 3. So that is how we apply this combustion equation shortcut. Okay? So that is the equation. This equation goes for alkanes only. Then we say this alkane undergo substitution reaction, chlorination reaction as well. So see how alkanes undergo chlorination reaction. It undergoes this chlorination reaction in presence of UV. So you now say chlorine, when CH4, for instance methane, react with chlorine, it will give us what? C. One chlorine will replace it. It will give us CH3Cl. So one chlorine replaces one hydrogen atom plus HCl. Then this is in the presence of ultraviolet ray, in the presence of light. Then this will also react with chlorine again to give us one chlorine will replace one hydrogen to give us CH2Cl2 plus another hydrogen chloride gas. Then this will also react with another Cl2, that is chlorine gas, that is chlorination reaction. One chlorine will replace one hydrogen atom to be giving you CHCl3 plus another hydrogen gas. So finally it will react with another one until the hydrogen atom it has finishes to give us CCl4 plus hydrogen chloride. So that tells us that chlorination of methane in the presence of UV gives us final product called tetrachloromethane. We put it into writing. When methane is chlorinated in the presence of UV, final product it will give us is CCl4, tetrachloromethane. We call it tetrachloromethane. So this methane we talk about, or this alkane we talk about, can be prepared in many forms. It can be prepared by reacting any alkene groups with hydrogen, that is hydrogenation reaction in the presence of what? Catalyst such as nickel or platinum. So when you react alkane with hydrogen gas in presence of nickel or platinum, it can give you alkane. It has a lot of methods of being produced. Now mind you that this alkane has its own importance. One is that alkane with carbon 1, methane, ethane, propane and butane. That is alkane with carbon 1, to carbon 4, they are gases at room temperature. Then carbon 5 to carbon 9, that is pentane to nonane, they are liquids at room temperature. Then alkane of higher carbon, that is carbon 10 and above, alkane of higher carbon, that is carbon 10 and above, are quasi solid. That is for this saturated hydrocarbon. Then we go to unsaturated hydrocarbon. Other unsaturated hydrocarbon, we have alkane and alkyne. Alkane and alkyne, this is alkane, alkyne, cycloalkane, and cycloalkyne. Okay? So, that tells us that why do we call it unsaturated? It's because they have double bond for alkane and alkyne have triple bonds. Okay? So, when it has double bond, the structure of this or the molecular formula of this CnH2n, then this one CnH2n minus 2. So, they have double and triple bond. Because of these double and triple bonds, they undergo into reaction. But this alkane that have only single bond, their reaction can only be combustion, chlorination, substitution. But this one can go into reaction easily because the pi bond in the double bond or the pi bond in the triple bond can easily be broken down to go into reaction easily. Okay? It is noted that alkane dechlorizes bromine water, the color of bromine water. And this alkane, such as ethane, is very, very important because one of it is that it is used in producing or in ripening fruits such as banana. So if you want to quicken the ripening of a particular fruit, you can use ethane and ripen it. Okay? Now, we also have other compounds which can be saturated or unsaturated. We have alkanol, alkanoic acid, and so on. We will still look into it. But we want to see what are the importance, what are the sources of these organic compounds. One, this organic compound can be gotten from dead and decayed plant materials. It can be gotten from vegetable remains. It can also be gotten from mining areas, and also it can also be gotten from animal droppings. These organic compounds, especially hydrocarbon, have its wide relevance that is used very well. It can be used in production of pigments as a barrier in living organisms. It can be used in production of colors. So it has a lot of wide